Hi, and welcome to my office. I'm going to be coding a simple Ethernet frame just to wrap up my data and send it off the Ethernet. And I'm going to show you the state machine that I've written to do that. So because this is quick and dirty, it's not going to have ARP support. It's not going to be anything fancy. All of the stuff is going to be hard-coded, and it's not going to work on every network. If you were doing this in like a serious application where you wanted networking support and all that stuff, it probably would be better to not do it yourself. It would be probably better to use someone else's stack that they've already made that has all the stuff you need. What this demo does is it generates a packet every second or two. There's a parameter that you can specify how often a packet must be generated. And that packet in this case is populated with a increasing number. So first byte will be 0, next byte will be 1, next byte will be 2, it just counts up. And this is great for debugging to check that all the bytes are there that you want to receive and making sure that everything's in order and nothing is corrupted and everything like that. So this is just a simple demonstration of how to do that. So this is my top level project. I have my top level ports. And then I have a reset generator, and the reset generator generates a reset from the input pin. And this also includes a little bit of debounce. And then these are the pull-ups for the boot mode configuration. There's no MDIO interface. So the reason why I can get away with not using an MDIO interface, and the MDIO interface usually configures the Ethernet speed and the features that are available over the connection, whether it's full duplex or half duplex, and whether it's 100 base T or 10 or a gig. In this case, these boot mode straps enable automatic line negotiation. So this particular value of 111 will enable the mode that's the automatic communication mode. That means that the FPGA will automatically negotiate the line rate speed with the MAC on the other side. And that's really useful. So I don't have to worry about it. And that also means I don't need an MDIO interface. I have a reset generator and a clock generator. That's the clock generator that has my output clocks. And then the clock and reset that I use for my Ethernet. This is the packet timer. So this is just a small timer that generates a pulse every second or two. So in this case, I have 2 seconds. I also have a define here where if it's simulating, then it will use a smaller value. And that just means that I can see packets more often when I'm simulating, because to wait 2 seconds between packets is a lot of time. It's a lot of simulation time. So instead what I do is I make it shorter, and then I don't have to wait as long. But then when it's synthesized, then the value is correct. And so this define just allows me to have separate values for the simulation and the synthesis, which is really useful. So this is just a packet timer. I specify how many bytes my payload's going to be. I count up to the maximum and then generate a pulse, which is this packet enable. There is an AXI stream interface here, and the AXI stream interface gets populated with just an increasing number. Just the timer counts up, and so the AXI interface will populate with those values. This is my packet generator instance, the number of bytes in the payload, which is specified here, and the destination MAC address. So let's take a look at what's inside this packet generator. So I have a few parameters. I have the source MAC address, the destination MAC address, the output interface width, which in this case is 2 bits, and the packet payload. And then on the inputs, we've got an AXI stream interface and the data out. These are a whole bunch of defines. I'm going to skip ahead to the state machine. So basically, the state machine has several states. The idle state is it's not transmitting, and then it goes through the different fields that make up the Ethernet packet. There's the preamble, the start frame delimiter, the header, the data, the frame check sequence, and the interframe gap, which is a wait period between packets. And these stages make up the Ethernet packet. This is what the Ethernet frame looks like. The preamble and the start frame delimiter are fixed values, and the header is Ethernet header. Then the data payload is the data that I want to put in, and the frame check sequence is a checksum that's calculated later, and then we wait before the next packet. And this is kind of the structure of my Ethernet. And so my state machine goes through each one of these states and puts in the appropriate data that it needs at that point. And above here, I have calculated how long it must remain at each step. All of these are fixed except the data and the header. And that's really nice. It's useful to change the length of time that it spends in each state. And you can use this for anything. So anytime you have a state machine and it's like this long in this state, and then this long in this state, and then this long in this state, you can configure it and do it like this. It doesn't necessarily have to be Ethernet. And so these are the number of bytes. And then because my output width is 2 bits and not a full byte, I have to stay in each state for 4 times longer. It's because it takes 4 cycles to generate a byte instead of 1. So this is the actual cycles that I'm going to be spending in each state. I have a header generator here, and that's this file, and it basically just populates the source and destination and type. Because this is a little Indian FPGA and the host, the Ethernet host that's receiving the data from the FPGA is a big Indian system, I need to flip all the bytes around. And that's what this does. It basically switches the Indianness of these fields. So that header generator just gives me the header that's all encapsulated. I have a data FIFO. So the data FIFO stores the data to be transmitted. The reason why I need a FIFO, I need to know that there's enough data waiting before I start sending the packet. If I start the header and I don't have any data, then I'm not going to be able to complete the packet. I need to be able to accumulate the data I need, and then I will transmit it with the header. This is because I'm transmitting packets below line rate, and that's what this FIFO is doing. So when data comes in on this interface, I store it in this FIFO, and valid is ended with ready, as it should be with the data. My ready is driven by not full, and so and that kind of makes sense. If the FIFO has space, then I'm cool to receive stuff, and if the FIFO doesn't have space, then I'm not ready. And that's nice because this is insulated from the rest of what's going on. So it doesn't matter what my state machine's doing. It doesn't matter what state it is in. The FIFO acts as like a nice little buffer between what my state machine is doing and what's coming in. So I can just like store stuff in the buffer and let my state machine carry on. And that's really nice. I'll talk about reading from the FIFO in a moment. I need a counter to keep track of how long I'm in each state. And then I have my state machine. FIFO count is how much stuff is in my FIFO. And if there's enough stuff in my FIFO to make a payload, then I'm cool to go. So then I head over to my preamble. When my preamble is done, I go to the starter frame and then to the header and so on. And so the state machine basically just chugs through every single state all the way down. And then I register the next state into the current state. And then, so at this point, I now have to decide what I'm going to do for each state. And this is what I like about using a state machine like this, is that you can set up a really nice framework for the outline of what your interface is going to do. And then per each state, you can decide individually what is going to be done during that state. And so it's a really nice way of anchoring the behavior of your signals to a specific state. And then you don't have to worry about them getting mixed up in between each other. And so in this section, I decide what data I'm going to be driving on my Ethernet interface per state. So every state has a buffer. And because the width of the output Ethernet is only 2 bits, I'm going to be shifting my buffer out 2 bits at a time. And so this buffer is the shift register that's going to be shifted out. For example, in the preamble section, the bottom 2 bits of the preamble buffer will be driven. And in the frame delimiter, then that buffer will be used, and so on and so forth. And so every state that drives data will have a buffer, and that buffer will be shifted out during that state. I also have some flags that are applicable, because in some states the data is valid, and in other states it's not. So I have a valid. During idle it's not valid, and during the wait it's not valid. And so that's a nice way where you can, for each state, choose, okay, this flag is this value, this flag is this value, and so on and so forth. In the case of this frame check sequence, certain states contribute towards the frame check sequence. So the header data is applicable for the frame check sequence, but the preamble and the starter frame are not. And that's how I flag those. And then additionally, the frame check sequence gets reset during idle. So that's the state where I'm like, okay, now I can reset my frame check sequence in preparation for the next frame. So these flags are useful. It's useful if you have a flag that you know you want to choose specific values per state. You can do that here. The state machine method that I'm using, by the way, is called the 3-process method. And there is a really nice paper by Sunburst Designs that goes over different state machine methods. This state machine method I really like. I find it really flexible and I find it really clear. And it's a really nice one for creating a framework. This section is where I set up those buffers. So previously here, I showed that every buffer shifts out during its state. In this process, I am setting up and shifting the buffers. So during the idle state, I drive the buffers with the values that they need to have in preparation for starting. So I populate the header buffer with its initial header value. I populate the preamble and the starter frame with those are initial values. So these buffers are being set up with their initial values so that when those states are reached, they can be driven out 2 bits at a time correctly. And those are what these sections are doing, these if statements. If I'm in the header state, then I drive the header buffer out 2 bits at a time. Preamble state, starter frame, those all behave very similarly. For the frame check sequence, I load the frame check sequence value into its buffer, and that is when the state changes to the frame check sequence state. And this is what I really like. I really like having a current state and a next state. And the reason why I do is because then I can detect state transitions. And that's why I choose the 3-process state machine method, is because the 3-process method gives me a current and a next state. And it allows me to not only know what state I'm in, but know where I'm going and where I'm coming from. And so in this case, I can detect the state transition from the data into the frame check sequence. And I'm using that state transition over here to detect that I need to load the frame check sequence value into its buffer. And that's the place that I do that. And then the frame check sequence also gets driven out just like it would usually. So the data is a little bit different, and I'll tell you why. Because my FIFO is an 8-bit FIFO. And so I have a whole bunch of 8-bit signals that are stored in my FIFO, but I need to drive those signals out 2 bits at a time. So I need to take a value, store it in the buffer, and then shift it out for 4 cycles, 2 bits at a time, and then get the next one. And so I'm going to show you how I do that here. So this is a special case. This is when I transition into the data state. So again, I'm looking at my data state in transition, where I'm transitioning into the data state. And at that point, I'm loading my buffer and I'm acknowledging that sample. And so that allows me to prep for the first sample that I'm not in the data state already. And when I'm in the data state, every 4th cycle, it will load a new sample. So in this case, when the state counter 2 least significant bits are equal to 3, which is high, then I will load the next sample. And that's because the state counter always starts at 0 for each new state. So 0, 1, 2, 3 will be the 4 cycles of the data being shifted outwards. And the 3rd one will always be the final shift for that word before the next one. So that's why I can use the state counter as my counter for reading buff signals out of the FIFO. And then the other 3 count values for those 2 least significant bits, which is 0, 1, 2, the data buffer is just driven out as usual. So I have a FIFO read enable here, which I also drive, and that is acknowledging, that's like the ready on an axis stream. It acknowledges the existing sample and it requests a new one. And so I'm driving that high at the same time that I'm getting the new sample. And that's all the buffers. So now I've set up all my buffers and I'm shifting out my buffers. So there's only one last little thing that we need to deal with, and that's the frame check sequence. So I have a CRC32 generator here, and the way it works is that you put in the data that you're transmitting, and every new sample it creates a frame check sequence for all of the samples so far plus that one. So you get a new frame check sequence every time because it doesn't know when it's going to end. So it just gives you a new one every time. And so when you do end, that's the one you use. And that's why from the transition into the frames check sequence state, I use that value because that's the value I want. I'm going to briefly show you my CRC gen. So this is the CRC generator. I used it from this website. Let me just look up the website for you. I used this website to generate it. Basically what you do is you put in CRC32 and you tick little endian because that's what the FPGA uses. And then you choose Verilog module, generate CRC code, and then it will give you this code. And so what I did is I copied and pasted these assign statements to here. So this is the frame check sequence. What the frame check sequence is it's a linear feedback shift register. I did a video on the linear feedback shift register. It basically is a pseudo random number generator. In this case, it's used to generate a checksum value that's used at the end of the frame, and that is what this does. Basically, all it does is it just takes the input data, runs it through this combinatorial linear feedback shift register, and then drives the output. And then if the reset is driven high, then it resets it back to its initial state, which is all ones. And that's that. And that's my CRC generator. And that just gets appended onto the end of the packet. And then I just drive my transmit outputs to the outputs of my modules. And that's the packet generator. Let's see how it works. So I've built it. There we go. And I have my Nexus board connected up here in Vivado. So I'm just going to hit program. My light is going, so excuse me. And that's done. And now I'm going to head over to Wireshark. I like Wireshark because it allows me to debug what the packets look like. You can see packets even if they've been malformed or if the frame check sequence is wrong or something like that. So it's nice to be able to debug. So if we take a look here, we can see, I'll just pick a packet and we can see the source and destination, MAC address, the length, and then the frame check sequence is good. So this is really nice. And we could see that the payload is increasing. It's counting up in value. And so that looks correct. And then there's the frame check sequence at the end there. There are a couple of things that you can do if you want to debug and you need to see the malformed packets and if there's some kind of problem. What I do is I go to my console, I type ETH tool and then the dash big K, the interface, and then RX dash FCS on. This will allow me to see the frame check sequences in the packets, and then RX all on will allow me to receive all the packets. So if you're using one of these adapters, it may give you an error when you run these commands. If you have one of these guys, you may not necessarily be able to run these commands. And the other thing you can do is go ifconfig enpos8 promisc. And that will also allow you to see packets that don't have your MAC address destination. So it will see all the packets on the interface, not necessarily the ones addressed to you specifically. And that's that. So I've put all my code in GitHub. And the nice thing about this is that any Axis Stream interface you can use to drive packets onto the Ethernet. And that's really useful. The only thing that I will caution you of is to check the Fifo overflow condition. Currently, I just have ready being driven by full, but that means that you could get corrupted packets if it gets full mid-packet. So I have sized my Fifo significantly larger than the packet size. It's like 10 times larger. And so that helps with that problem. But just be aware if you're going to be sending larger packets that you could corrupt a packet if the Fifo is full mid-packet. And that's something I haven't taken into account here, and that could be a problem for you if you use this in the future. So just if you do go down that route, just make sure to watch your packet size and your FIFO full, and just make sure that you aren't corrupting packets that way. I'm hoping to expand upon this and maybe do some other data off this Ethernet interface in a future video. So thank you very much for watching, and I'll see you next time. Bye!